Okay. Now, let's see this next slide. Find out where that is. We already done that slide. Yeah, we did. Okay. Next one after that is here. I think that's where we start today. Okay. So, let's see, do we start there? Not actually. So let's get this one open. Okay, let's get a pen selected. All right. First, I can't remember if all of you were here last time, but I made the proposal, and I've got to check with my boss and make sure this will be okay. But unless otherwise noted, because we need to be out of town, my wife and I need to leave town on the Thursday before the weekend, Thursday of the weekend before the 4th of July. So the last Thursday in June. We need to be on the road before I could get home here after, 5:30 or 6. So I had asked if it would be all right if we did 30 more minutes of class from 5:30 till 6 for next Tuesday, next Thursday, and the following Tuesday, and then we won't have class on the Thursday. So we'll have our hour and a half in, but not have class on that Thursday before the last Thursday in the month. Is that all right with everybody? Anyone who wasn't here, who wasn't in on the discussion, is that okay? So we'll go for the next 3 meetings after tonight, Tuesday, Thursday, and Tuesday of the following week, we'll have 4 to 6 rather than 4 to 5:30. Okay? All right. Well, then we'll plan for that. I need to check with my boss to make sure it's okay with him too. But I wanted to get that on here too. Next, are there any questions on anything we've covered so far? All right. And another thing is, before you leave tonight, be sure you pick up the test for Chapter 8, because I've got it ready, and a few people picked it up Tuesday. I want to give it to the rest of you tonight. All right, we're doing example 1 on page, actually, I think I'm going to get out of this, because I think the previous illustration will serve me better than trying to draw my own, but I can't get it. Ah, there we go. So let me go back to, maybe it's easier doing it from here. That one. Okay. Okay. I think this will do well for this one. So let's do it from current slide, and we'll go from here. No questions? We're on example 1, top of page 220. It's Chapter 8, Working Energy, and this section here, it's funny they don't list that, is Conservation of Mechanical Energy on page 220. And here they're talking about a pile driver falls freely from a height of 3.5 meters above the pile. Well, let me get my pen activated. I thought I had it, but I changed slides, so let's get it back. So here's the pile right here, okay? And the bottom of the pile driver is going to fall from, say, somewhere up here, okay? So that height that it's going to fall is 3.5 meters. I think it's 3.50 meters, okay? 3 significant digits, okay, above the pile. What is its velocity as it hits the pile? What we're interested in here is V on impact. So I'm going to call that I for impact. What is its velocity there? Now, two approaches here, at least two. One, we could go back for conservation of mechanical energy, or the second is just use the formula we came up with. It's up to you which way you want to go. Second? I can't hear. Okay, I hear a formula coming out here. V is equal to square root of 2GH. Very good. Now, things to look for first, your height. This is what this is. That's your height of 3.50 meters. So that's in terms of H. We know G in terms of meters, SI units. G we know in SI units. So why not let's stick with SI units. So our velocity now should come out in meters per, no, I'm sorry. What? Velocity in meters per second. That's what it's asking for. Yeah, right when it hits the pile. So velocity will be in meters per second. So that'll be the square root of, what is your G in SI units? 9.80. What units? Meters per second squared, times your H is 3.50 meters. Okay. And I think I'll need calculator help on this one. But while you're doing that, let me note the units. Meters times meters is meters squared, and divided by second squared, and when we take a square root of that, what would be the unit? What would be the units? Meters per second, a great unit for velocity. So someone punched it in the calculator yet? It's 2 times 19.8, which is, 2 times 9.8, which is 19.6 times 3.5. Can't. Second? And when you take the square root, is that? Okay. So with the square root involved is about 8.28 meters per second. Okay? Let's see how they did. Oh my goodness, look at that. They got the right unit. They got the right answer as well. Make sense? All right, good deal. Now, the next little part actually comes on the next slide, this one. Conservation of mechanical energy can also be illustrated by considering a swinging pendulum, okay, where there's no resistance involved. Now, the two types of resistance you could have and do have is your pin up here. If there's any resistance that's all there, you're going to lose a little. And there's always some resistance, but we're going to mark it negligible. The other thing is whether there's any air resistance, okay? And there's always a little bit of that too. But we're going to count that negligible here too. And Jalen is here. Good deal. Now, where do you usually see pendula most frequently? Anyone have a clock? Okay. How would you describe the pendula in the clock? Okay. They're usually, ours in our house, sort of big and round like this as you look at it. When you look from the side, they're very, very thin. Okay? And since they go back and forth, that very thinness is going to minimize air resistance. What's more, the clock is enclosed in a glass case. So there's no moving air in there at all. No wind and something to be more air resistant. So they do everything they can to minimize that air resistance. And then the pin up there usually is pretty well, if it's not well lubricated, it's a very nice bearing that goes pretty well. So for now, we will count this as frictionless. There's no air resistance. Okay? Now, it says pull the pendulum over to the right side so it makes an angle of 65 degrees with the vertical. I kind of hate they said that, okay? because what follows and the formulas they're going to use basically depends on it being a small angle, as in just a few degrees. In most grandfather clocks, that angle is quite small. So this is a bit of a stretch to say 65 degrees is large, but we're not going to argue with them, okay? At this point, the pendulum contains, what would you say? At that point, you just pulled it over there and kind of are holding it there, okay? So what is its energy at that point? What kind of energy? Potential energy, gravitational potential energy, because as low as that could go would be somewhere down here, right? So the difference in height between the low as it can go and where it is now, that's your H, okay? And what is your formula for gravitational potential energy? I like to call it GPE. They call it just E sub P, which is fine, but there are other forms of potential energy. Gravitational potential energy says it most directly. What's that formula? Is what? mgh. Perfect. Mass times acceleration due to gravity times the height. And the height would be the height above the zero reference level, as low as that can go in this given problem. Or any other level, you just subtract it from that, okay? Now, let's see, I don't think they show, yeah. When it moves there, what can you tell me about its energy? You've released it now from the dotted position and let it fall, and it's frozen right there. What can you tell me now? If this is as low as it can go, okay, it still has some potential energy, but it's less now because your H here is less than it was a while ago. In fact, it looks like it's about half. Where did that potential energy go? Say again? Okay, it did decrease, but you can't destroy energy. What happened to it? Say again? Up here, you were holding it at rest. When you let it go, what does it start doing? Moving. And what's the energy of motion? Kinetic energy. And what's the formula for kinetic energy? I don't mind E sub K. I usually call it KE, but that's E sub K is fine with me. 1/2 mv squared. Okay, very good. Okay, get my roll book. Is it Katisha?
Yes, sir.
Okay. All right. So we're still missing Mackenzie, Cece, Maya, and Tiffany. Okay. All right. So if that is half the height it was before, then you have half the potential energy. That's easy to do. You already calculated potential energy up there. Take half of it. The other half of it is your kinetic energy, because those are the only two forms. The sum of those is mechanical energy. Okay? So the graph here illustrates that it's 50-50 there. So from that, if you know the kinetic energy there, you can find out what the velocity is. Okay? They don't ask that now. Okay, what can you tell me about the position down here? Anything? What's that? Yeah, it's not resting. In fact, when you release it up here, it's maximum speed here. But right now we took a photo right when it was at the bottom. What can you tell me about its energies there? First, second, absolutely more kinetic. In fact, if this is indeed as low as it can go, which it seems to indicate it is, then the potential energy is gone to zero. relative to what it had before, because that's your zero reference level. If it can't go any lower than that, that we consider your zero potential energy, okay? Gravitational potential energy. So the kinetic energy is max right there. If the kinetic energy is max, what else is at its max? No, potential is zero. It's at its minimum. What does kinetic energy depend on? Say again? Velocity is at its max. It won't ever be any faster than that, because as soon as it passes this position, it goes here to the next position right here, and now it's gaining potential and losing kinetic. So it's losing speed too. And when it gets up to this position, what can you tell me? The potential is the max, so it can't go any higher. And that should be, if the original is correct, that should be about 65 degrees. Again, I think that's too large an angle for this to be working, but all of the energy has gone back to being potential, no kinetic anymore. So all along the way, it's losing one, gaining the other, gaining one, losing the other. But the mechanical energy is constant, zero, the sum of the two. So they left off this one here, well, they left it off in the book too. There it would be back the same potential as here, and that was a couple slides ago, there, and half the kinetic, half potential, okay? And then here you're back to all potential, zero kinetic. So it stops there just momentarily and then falls back again. Should be over here. Okay. Does that kind of make sense? Okay. Mechanical energy is conserved, the kinetic and potential exchange constantly. Maximum potential, gaining kinetic, losing potential, lost all the potential, all kinetic, starts losing kinetic, gaining potential, till it's all potential, loses all its kinetic. Okay. Now, here is example 2. Wow. Strange problem. No picture for it. So let's make up our own. It's not the roller coaster yet. It's okay. Go back to this one. Sorry, this takes a while to swap slides. Okay. It says drop a 5,000 kilogram mass from a hot air balloon 400 meters above the ground. Find its kinetic energy, its potential energy, and the sum of the kinetic and potential energy in 1 second intervals until the mass hits the ground. Okay? Wow. Okay? That's a lot of finding. Let's not do them all. Let's just do a few. You okay with that? All right. So here we have a hot air balloon. Okay? Here we have the little basket underneath. Okay? And here we have you dropping a huge mass. Okay? This is almost a crazy problem. You know how much 5,000 kilograms is?
So is it something that we need to know?
No, but I just was wondering. 5 tons. Do you know any hot air balloons that can lift 5 tons off the ground? Not really. Okay. So this is really kind of a crazy problem. 5,000 kilograms. Oh, I'm sorry. My eyes are bad. That's 5.00. Not so bad. Sorry about that. So here's a mass. Still a pretty good sized mass. You're going to drop that from the balloon. And this has a mass of 5.000 kilograms. 4 significant digits here. From a hot air balloon, and this hot air balloon is 400 meters again 4 significant digits, above the ground. Okay? And it says find its kinetic energy, its potential energy, and the sum of the kinetic and potential energy in 1 second intervals until the mass hits the ground. Assume no air resistance, which is probably going to be a little bit faulty too. What other piece of information do you need here? We know it. Well, we'll get to the thing. Which you want to do first? Kinetic energy, potential energy, or the sum of kinetic and potential energy? And where do you want to measure it from? What is the easiest thing to get, just given the information we have here? Hint. Mass, this is height. What do we almost have? Potential energy. And what is the gravitational potential energy? Is what? MGH. MGH. And the M is 5.000 kilograms. What's a G? 9.80. What units? Meters per second square. That's an acceleration. And the height? 400.0 meters. Now, here's the deal, folks. Why have those extra zeros in there? No real reason, because we only got 3 significant digits with the acceleration due to gravity. So having that extra zero in the 400 and 5.000 kilogram does us no good. We can only have 3 significant digits. But let's calculate what it is. And by the way, this is right as you release it, before it's fallen. This is the MGH there. Someone punch that in and see what you get. That's 2,000 times 9.8 would be 19,600, right? Is that right? 19,600. What unit? Second? No, none of them cancel out. Kilogram meter squared per second squared. Joules, exactly. Okay. Let me get CC here, right? Okay. All right. Now, 19,600 joules. And we'll leave it there to begin with. That's the GPE at the top. Maximum GPE it can have. What else is that? At the top. Now, that's potential energy, gravitational potential energy. But what other energy is it? Say again? We already said potential. What other energy is it? Okay, here's the other hint. You're dropping it. You're not throwing it. Mechanical. You're absolutely right. This is also the mechanical energy at the top. GPE at the top and mechanical energy at the top. Okay? So what's the kinetic energy at the top? What's kinetic energy at the top? You dropped it. You didn't throw it. You dropped it. Second? If you drop it, what's its initial velocity? Right when you open your hand. What's its velocity? Second? 0! You didn't throw it. That would have given it initial velocity. You dropped it. So the KE, you mind if I use that? I just like these better. At the top is 0 because its velocity is 0. That's why all the mechanical energy is gravitational potential energy. All right. Now, they say calculate these same 3 things: kinetic energy, potential energy, and the sum of the kinetic and potential, which we call mechanical, in 1 second intervals. So what do we know happens 1 second later? Yeah, it's going to be dropping. Okay. Now, what can we use to measure something about that drop? Second? Okay, half may be in there. There's halves in a couple things. Basically, what's changing here, as it drops, which of the variables we got on the board is going to be changing? Will the mass be changing? No. Mechanical energy won't. The height will be changing. You're absolutely right. So we need a formula or an equation that tells us the height at any time t, because we're going to do it at 1 second later. You remember what that is? H of t. We may not have put the t in there. Maybe I shouldn't put it in there now. What's that formula? And that has a half in it. Say again? Okay, that's kinetic energy. Okay, we're not ready for that one yet. What is the height at any time t? Hint, this is back in chapter 5. Okay? You remember? Sort of Galileo's formula? Anyone remember it? How about 1/2? It does have a 1/2 in it. GT square plus V0T plus, now here's the deal. What's that? Okay. Back in chapter 5, wasn't it? Okay, let's see, chapter 5. Let's see if we can jog some little gray cells. Okay. All right. Maybe we didn't do that formula, because that would have been in preliminary stuff. But did they give it to us at some time? And we were working a problem. I don't remember it. I'm teaching physical science also, and I can't remember what we covered in that as opposed to this. And I'm teaching 4 math courses, and we do these kind of problems in them too. So maybe not. Sorry about that. Okay? I guess we did it here. Well, here's the formula. Okay? H of t is equal to this, and this would be H0. Now here's the problem, folks. We want the height from the ground, so it has to be decreasing. So what we're going to have, this is going to be negative because gravity is pulling downward. This actually is 0 because your initial velocity is 0, so you don't have to worry about that term. And your H0, that's your initial height, that's 400 meters. Okay? So basically, all you have to do is do negative 1/2 GT squared. That's going to be a negative number, subtract it from, put a 1 in there, okay, and subtract it from 400. So it'll be negative 1/2. And when you square 1, what do you get? 1. So it's 1/2, 9.80. Okay? I'm going to leave off the units for now. So that's going to be minus 4.9 meters per second. Because 1/2 is squared, that's just meters. So subtract that from 4.9, from the 400. Okay? And that will give you 395.1 meters. Okay? Now, let's do it once, maybe another time if you really need to see it, but after a while, in 1 second, the S is 4.9 down, the V, I don't know why they're giving you V, Okay, the H, that's what we got here, 3.95. So do the EP, the GPE, that will be the GPE at 1 second is going to be mg times 395.1 meters. Okay, so that same mass, 5.000 kilogram, times the same g, 9.80 meters per second squared. Okay, multiply those together. Just like you did before, but this time the height is 395.1. Well, it's just what m was. M is 5, and g is 9.80, just like before. Just to give you the numbers you can put in. So what's your GP at the top?
So we're doing a 9.8. Oh, no.
5 times 9.8. Same first two numbers. It's just instead of 4, you're doing 400, you're doing 395.1. Okay, 9.80 meters per second squared is the acceleration due to gravity always. Okay, your mass hasn't changed. That's still 5.000.
It's 19,359.
Okay, 19,359. Is that what you said? Okay, now we're not going, let's see. I guess for your answer, we need to do it, that'd be about 19,400, right? So let's just say 19,400 joules. That's okay. I'm real tempted to leave it 19,359. Okay. So in other words, we lost some gravitational potential energy, right? Now, our mechanical energy is still 19,600, right? Mechanical energy is conserved. It doesn't change, okay? So the answer to every mechanical energy is going to be that right there. This is your gravitational potential, so let's subtract, let's go back to your 19,359, okay, and subtract 19,600 from that 19,359. Okay, and that will give us a 1, a 4, and a 2. So 241 joules will be your KE at 1 second. Okay, and that's all you have to calculate. They did a lot more in your book than you have to do. Okay, so you have to calculate the GPE 1 second. Okay, you have to calculate your height 1 second later. Okay, that's from that formula. Okay, then you have to calculate your height, your GPE using that height, and then subtract that from your original mechanical energy, 19.6, and you got it. Okay, so that'll be 241 joules. Yes.
You subtracted the 19,600 minus the 19,350.
59, yeah.
You don't subtract the rounding part?
Okay, yeah. I don't round it until I'm writing my answer down. And since I haven't calculated KE yet, I'm going to keep those digits, calculate it, and then round. And this will round to 241. I got 3 digits there. This rounds, when I put it in the table, 19.4. Okay, so 1 second later, they get, for some reason, they rounded to 240, and the EP was 19,360. Now, they did 360, and I don't, okay, they're doing it wrong. I don't mind that they do it wrong. I'm happy with 359, okay? This is joules too. But you see, they only have 3 digits in here. And they wrote it in the book that way. And yet they're rounding to 4, which is fine. You can round anywhere you want to, but precisely, you don't have it. But 3/5, yeah, that's perfectly fine. Okay? So, that was 1 second later. To do 2 seconds later, we go back to just like we did before. Now we're just doing -1/2 g t squared. But this time t is 2 seconds. So -4.9, that's half of 9.8, 4.90 times 4 seconds squared. Okay? And I'm not going to put my units. So 4. When you double 2, you square 2, you get 4. So 4 times -4.90, 19.6. Is that right? Is that right? $19.6? You get it? Okay. Subtract that from my 400. So the 400, that's the original height. Subtract 19.6, and I get 380.4. Is that right? 380.4 meters. Okay. Now I calculate my GPE there. GPE at 2 seconds is going to be your 5.00 times your 9.80, this time times 380.4. So you see, each time you're putting a different height in there because it's fallen, and that's how high you are now. So what would that be? 18,679? 639. Any point? Huh? 0.6? Let's make it 40 then. Okay? Because there's no reason carrying around too many digits. Okay, this time subtract that from your original, which was mechanical, where there it is, 19,600, and you get 960, yeah, 960, okay, 960 joules. That's your KE at 2 seconds. Okay, so your gravitational potential is decreased, your kinetic energy is increased. Okay, got it? Okay, get it? No, I'm just kidding. Okay. All right. Have y'all got the numbers down, somebody? Let me try to set up a table and make it maybe look a little better. Okay? I'll take out my drawing and everything. You got that. I just don't have enough room to write on the screen. So what we're going to do each time, we're going to do time here. Okay? And this will be in seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm not going to do all those with that. Okay. The easiest thing to do then is calculate your height at each of those times. Okay? Well, first we'll calculate the height that it fell. Yeah. Let's see, what do you want to call that? The distance it fell, let's call it that. Distance fallen, okay? Then we'll calculate its height at that time. Then we'll calculate the GPE at that time, and then we calculate the KE at that time. Understanding that the mechanical energy that we already calculated was 19,600, I can't write, joules, right? That was your original energy, okay? Now, distance it fell to begin with, what was that height? I erased mine, but I told y'all to hang on to it. Huh? 4.9, was that it? Seemed like it had another digit in it, didn't it? Oh, you're using theirs. Okay, 4.9. No, they call it S. Okay, I'm sorry. That's the height it fell, and they're calling it S. I'm okay with S. Distance fallen is fine with me, too. I don't care what you call it. But they're calling it S, so I'll call it S. Okay? I'm agreeable. Okay, and that would be meters. So the height is basically 400 minus S. So this is your 395.1 meters. Then you use that for your GPE. I'm going to show you GPE again. GPE is equal to mgh. Your mass doesn't change, so that's 5.000 kilograms times 9.80 meters per second squared. And then you put your height in here. That height was 3.95, or 395.1. Multiply that together, and that gives you your GPE. And what was that? Someone wrote it down, I'm sure. 19,000. Say again? 351. 3 what? 59. Is that what you said? Okay, and that's joules. Now the KE is always ME minus GPE, because the sum of those is the mechanical energy. So subtract this from your 19,600, and that gives you your, what was that? 241, wasn't it? 241 joules. And mechanical energy stayed the same, right? All right. Now, how you do S, that's a key element here. So here's your S. S is equal to minus 1/2 GT squared. So for every time you enter. So the next time, that was, you can make this a minus if you wanted to, okay? Did they in the book? They didn't. They just called it positive, okay? 1/2 GT squared. This time T is 2 squared. That's the one we just did. And what did that come up to? 19.6 meters. Subtract that from 400, and you got 380.4 meters, right? Okay. Plug that into here. Same 5,000 times 5 times that. This time you multiply by 380.4 mgh. That's your new h. These two stay the same. Just multiply by that, and that gave us 19,000. Or was it 18,000? 18,300. I don't remember. What?
No, we don't 5.000 times 9.80 times 380.4.
Yeah, 380.4. We did it earlier. I just had to erase it to get more room.
I got 18,639.
18,639. Okay, that's 640, right? We rounded it. Okay, subtract that from our 9,600, and that gave us 960. Is that right? We did it before. I'm trying to remember.
So we subtract the 18,640
From 19,600.
960.
960. Okay. All right? Now, you just continue doing that. Okay? 3, 4, 5. You want to jump up to some other second? You don't need 10 and 11, obviously. They showed it. Whoa, get back.
My question is, like, on the 2 seconds, it went from the 4.9 meters at 1 second to 19.6.
Right.
That's what I got.
Okay.
On the other one, I didn't get a chance to write it all down. Like
Okay.
I did before.
Okay. Here's the formula. That's it right there. The first time you do S is equal to, we'll just leave off the sign for now, 1/2 times 9.80 times 1 squared. And 1 squared is 1, right? So this would be half of 9.80 is 4.90, right? And that's where that came from. Okay? And that would be meters. Because this is meters per second squared, and this is second squared. Okay, so the second squares cancel out. The next time, it was S is equal to 1/2 times 9.80 meters per second squared times 2 seconds squared. Well, 2 seconds squared, second squared, those cancel out again. You're left with meters. Okay? And it's 1/2 of 4, because when you square 2, you get 4. And what I did before, I left this as 4.9. 1/2 of 9.8 is always 4.90. Multiply that by 4. That gives you 19.6. Okay? So for 3 seconds, you go right in here. S is equal to 4.90. That's half of 9.80 times, and now 3 squared would be 9 square seconds. Okay? So it multiplied by 9. So 4.90 times 9. Anyone punch that in quickly? It looks like 44.1 meters. Subtract that from 400. 355.9. Plug that in over here. 5 times 9.8 times 355.9. Was that 17,000? What?
17,439.
Okay, 17 or 16?
17.
17, and what was the rest of it?
439.
439. Let's just leave 439. Okay, subtract that number from your 19.6. 2,161, let's call it 61. Okay, so you see it's rapidly losing gravitational potential and gaining kinetic. Next time for second 4, start again here. S is equal to 4.90. Goodness gracious. Okay, times, this time you square 4 and you get 16. So multiply that, 4.90 times 16. I can't do that in my head. Right. 78.4 meters. Subtract that from 400, and you get 321.6. Okay, meters. Plug that in over here. 5 times 9.8 times 321.6. 86 what? 12,086. Okay. Okay, I think we got something wrong there. We're going to have to correct, check that. Okay. All right. Yeah. 15,758. Okay, leave that off. Okay, kinetic energy, subtract that from 19,600. Okay, yeah, I know they're rounding. I'm just leaving the digits as she calls it to me. But every time you can go back and correct these to 3 digits. They're doing 4, which they don't have the right to do, but it's fine with me. Okay. And when you subtract that from 19,600, 842. I know they're rounding differently than we do. Okay. The next at 5 seconds. Again, you do your S is equal to 4.9 times, I'm leaving off the zeros, 25. So you keep doing like this. You just square the time, multiply by that, put that number, subtract that from 400, take that number, put it in this equation, and then subtract that from 19.6, and you got it. Just over and over and over again. You could get a computer to do it real easily. Okay? Let's do 9 seconds and see what it does. At 9 seconds, you would have S is equal to 4.9 times 9 squared is 81. What does that give you? 306? 396.9. Okay. Let's call it 397, okay? Okay. Now, subtract that from 400. Oh, let's leave your 396.9. Okay, sorry. And that would be 3.1. So its height is 3.1 meters. Plug that in over here. Not much kinetic energy, gravitational potential energy anymore. 5 times 9.8 times 3.1. 151.9. Okay, we'll live with that. And then subtract that from 19.6.
19,448.
Let's call it 448. Okay? We don't need that many digits anyway. But here's the deal. Almost all of it is kinetic energy now. You're only 3 meters above the ground. That's about the height of the ceiling. In another second, you've already landed. Okay? I don't want to be under it catching it because it's going pretty fast. We haven't calculated that. But that's what you do there. It's the same formulas over and over, just changing the numbers. Seconds to get your S. Subtract that from your 400. That gets your H. Use the H in the GPE, MGH. That's the only number you change. Subtract that from 19,600 because that's your mechanical energy. It gives you kinetic energy. Now, in the book, they also calculated the V. They didn't ask for V. No reason to do V, but you know how to do it. You square root of 2GH. You could have done that. But they didn't ask for it. So why do it? I don't know. Okay? And then that gives you, and your total should always be 19.6. So don't go back and add them. You know, you got it. All right. Enough of that. Now, the next figure, can I erase it? Okay, right, sorry. Ooh, I can't get that out of the way, but I'll leave it on there. Got it? Everybody? Okay. Okay. Now, why? All right. They just sort of throw this in at the end. Have you ever been on a roller coaster? I never have. I don't even want to. I get queasy at the stomach watching it, you know, so I don't know what I'd do if I was on it. I'd probably be okay, but I just have never had the desire. Okay? Now, if that's the roller coaster, what you have to do is get it to its highest point. And what they usually have is a, they call it I think they call it a tractor or something like that. to haul it to the highest point. That would be P. Okay? And they haul it to P. Now, your reference level is as low as it can go in the problem, so that's a little red dotted line there. Okay? You haul it to P, and then maybe give it a little push to get it off P. Down it goes. And it goes down almost to your reference level, hopefully not quite, and then goes up again. Well, as long as you don't go above P, see, up here it's all gravitational potential energy at P. And when you give it that first little shove, you might get a little bit of kinetic energy, but now it's gaining kinetic energy, losing potential energy till you're almost at your zero level down there. Then you start going up. You still have plenty of kinetic energy left to get you over that and around through there, and you stop there. Then you haul it up again and push it and let it go. That's how they work. And where are the thrills? In the acceleration. When you're changing your speed real quickly. Coming down, you're changing speed really quickly. When you hit that bottom, going, you're changing acceleration, because now you're going from very fast and start slowing down, and then up here and there. So all the way, when you're changing the acceleration, that's what the thrill is. If you're going along at 500 miles per hour, but it's a constant speed, you really don't notice it. When I was in the plane, flying to and from Rome or Brussels, wherever we were flying from, or Amsterdam, we're going really fast. But as long as it wasn't accelerating, you didn't even notice it. Okay? Now, if you hit a bump and you drop suddenly, that's an acceleration. You notice it. Okay? So on the roller coaster, if that's just a gentle thing like this, well, a change going around a curve, that's thrilling, isn't it? Because you're accelerating around the curve. You're changing your direction, your velocity. So that's exciting. But if it was just going like this, yay. How much did I pay for that ride? Okay. So not really worth it. So that's the thrill, is your acceleration. Now, they do make one other statement here. And by the way, all along the way, the kinetic energy plus potential energy is your mechanical energy. That never changes. Okay? At the top here, it's all gravitational potential. Down here, it's close to being all kinetic. Up here, it's maybe 50-50 or so. Down here, it's zero potential. Zero potential, all kinetic. They have to bring you to a stop, or you just keep on going. And as long as you didn't have friction, you could go forever. But you always have friction. Okay. Now, the one other thing they say here is, in an elastic collision, the total kinetic energy in the system before the collision equals the total kinetic energy in the system after the collision. So they've introduced a new word here, an elastic collision. An elastic collision means there's no deformation, permanent anyway. Things collide and they bounce back with the same kinetic energy they had before. Always. Okay? And they give you some formulas there, but they don't put it to use. And they have backyard physics, and the problem set here is in 8.4. Do any of the odds 1 through 13. Okay? I would do some of each, as many as you'd like. 8.5 here is alternative energy sources. It's a fun read. It's really short, but I really don't think you need it for sonography. I'm not sure. Do you? What you reckon? I don't think so. There are no problems for it, so let's move on. That finishes all we're going to do in the chapter. It does have some review questions. It has all its formulas there, 8.1, 8.2, 8.3, and 8.4. And it has the review questions and review problems. The review problems will be fairly similar to those that you'll see on the test. There are more of them there than you'll see on your test. And then there's sort of an applied concept where they have a loop-de-loop loops in that looks like Six Flags roller coaster. Okay? Wish I had the time to tell you about my trip in an airplane when they were doing loop-de-loops. But I just as soon forget it anyway. Okay, Chapter 9 we're not going to do. Rotational motion, I don't think you need that in sonography. Chapter 10, simple machines, I don't think you need that in sonography. These are all fun chapters. That's Chapter 10. Oh yeah, I said it right. 9 is rotational motion. 10 is simple machines. 11 is universal gravitation and satellite motion. Interesting stuff, but I don't think necessary for sonography. So we're moving on to Chapter 12. Okay, matter. Now, before we go there, let me, I was tempted to pause this, but I don't think I need to pause it. What I need to do is find the test and give anyone that was not here and picked one up last time. Let me see. Has everyone turned in your test? No, I don't think so. So I can't return your test 1 to you. And what makes them using your other name, I have 2 Stricklands in the class now, so that makes it hard. Okay, did everybody get the test 1? Okay. All right, test 2. Did anyone not get test 2 last time? Okay. Notice test 1. Oh, it was even plot, huh? Okay. Oh, another even plot. I get more easy questions. Okay. All right. What's that?
I think she needs one. Person sitting next to me.
Oh, yeah, okay. She didn't get it last time? Okay. Everybody else got one? Okay, I have 2 left over. Let's see, that would probably be Mackenzie. Oh, I forgot to put Mark CC here, and Maya. Maya never came in, so I think I got the right number. Okay. So let me mark CC here, since I know I saw her come in, and she's still here. But Maya didn't make it, and so far, Mackenzie hasn't made it. Okay. So let me get out of, there was a loop-de-loop roller coaster. Okay, we're going to get out of this one and go back to this slide and go to whoa. That's so bizarre. They rearranged the chapters. I hope that changes back. That's so confusing. All right. So let's go from current slide. Okay. Now the reason we're doing this, I can't remember exactly how your course description read, but it said something about matter. And I just don't remember how it read. So that's what we're talking about now is matter. Does it matter? Okay. Chapter 12. Okay. And if you're in your text, it's on page 310. All right. Let's talk a little bit about verbiage now, so we'll know what we're talking about with these different terms. Matter is anything that occupies space and has mass. That chair, a desk, a table. Air occupies space, it has mass. Okay, water, that bag, whatever, a pencil. Okay, that's all matter. Okay. Now, way back historically, there was a guy, a Greek, named Democritus, way back, 400 BC or so, some way back, okay? And he had this thought process. He said, what if I had a piece of iron here? And what if I broke that iron into 2? And then broke it again, and broke it again, and broke it again, and kept breaking the smallest piece down, and just kept breaking, At some point, he said, I've got to reach the smallest little bit of matter I could get that would still be iron. Otherwise, there has to be a limit there somewhere. Okay. And he said, that last little piece, you can't break it any further. So he called that little piece of iron or whatever he was thinking of an atom. That meant in Greek, indivisible. Okay? Now, maybe a couple generations later, maybe 100 years or so, along came another really powerful thinker named Aristotle. Now, who's ever heard of Democritus anymore? Very few. Aristotle, just about everybody's heard of. He said, no, I don't buy that. I think that matter is a continuum, that you can't get to the smallest piece. You can just always keep breaking and breaking and breaking ad infinitum. It'll always have a smaller piece. So no, there's no such thing as a smallest piece. So Democritus fell out of favor and everybody believed Aristotle. Well, Aristotle also said that nature is made up of only 4 elements. He said there were earth, wind, fire, that's a singing group, what? Okay, and water. Okay, earth, wind, and fire, and then water. Okay, now, if Aristotle said it, everybody believed it. They thought those are the 4 building blocks of nature. Everything was made out of those 4 blocks. Okay? Well, then about like 2,000 years later, the science was beginning to take shape, and some of these dudes said, hey, if you can make anything else out of those 4 elements, earth, that's cheap. Fire, that's cheap. Wind, that's cheap. Water, that's cheap. Hey, let's start mixing and cutting and mixing and combining and heating and diluting and doing whatever it is, and we'll make gold out of those 4 elements. Because gold is valuable, and platinum and silver and copper. If we can make it out of those 4 elements, we got it knocked. So they started doing this. And these guys were called the alchemists. Okay? Early chemists. They didn't know they were, but they were early chemists. And they found out they better keep pretty careful records or else they'd keep doing the same thing over and over again. So they kept taking records, and they found when they combined certain things with water and heat and stuff like this, they got some new materials. They never got gold, never got anything very valuable, but they kept really careful records. And after a while, they said, there's something else going on here. There are more than those 4 elements. Okay? So, what we came up with then was, and he was just one of them, a guy named Lavoisier, French, came up and said, hey, I've identified, and I can't remember now what it was, 36, 56, something like that, elements. And he had a lot of the common ones down pat. He had a few wrong, and he had some that were totally wrong, that weren't even elements, okay? But he had the bulk of them in pretty good shape. Then over the years, more and more were figured out and added or deleted to it. And they found out a lot of these other things were elements combined together, but in totally changing, almost earth-shatteringly different ways, okay? For instance, does anyone know what sodium is? Sodium is a soft metal. That doesn't seem to make sense, but that's what it really is, a soft metal. I don't remember what color, sort of grayish maybe or something, but you can't ever, ever, ever let it get exposed to water, okay? Because if you ever expose sodium to water, it explodes, okay? Because it forms a new compound, sodium hydroxide, and that gives off it does explode. So if you ever are in a chemistry lab and you see sodium, it's always in a bottle with something on top that's oil, because you can't let the sodium get exposed to water. Okay. If you were to have a piece of sodium in your hand, you immediately have a burn because it just sucks the water out of your tissue and gives off a lot of heat in the process. Really dangerous stuff. Okay? So there's sodium. It's an element. Okay? Here's another element called chlorine. Anyone ever heard of chlorine? What is chlorine? Okay. We say that we're putting chlorine in the pool. We're putting really something more like Clorox in the pool because what we're trying to do is kill bacteria and stuff so you don't get sick, E. coli and other types of stuff like that from being exposed to it, and pink eye and all sorts of stuff. So they put, it's more like Clorox, which comes from chlorine. I mean, it's a compound of chlorine, okay? Well, what chlorine is itself is a poisonous green-colored gas. You don't want to breathe it, okay? You'll sometimes see tanker cars with chlorine and all sorts of warning things. And every now and then, if there's a derailment, if there's chlorine in one of those tanks, everybody evacuates because it's a poisonous green-colored gas, okay? So here you have a soft metal that will completely explode in the presence of water, combining with a green poisonous gas, and let's say that metal is sort of grayish color, and when they combine chemically, I don't mean you're just mixing them together, they combine chemically, what do you have? Salt, sodium chloride. I bet you've eaten some today, haven't you? What's in the bag right next? Oh, those are candies, aren't they? Oh, okay. Anyone eaten any chips today or something like that? Just about anything you eat has salt in it. You can eat salt made out of a poisonous explosive metal and a green poisonous gas. You can eat simple table salt. That's what a chemical reaction does. Changes things completely. Okay? So, that's what a compound is. A molecule is the smallest unit of a compound. For instance, NaCl, that's a molecule of salt. Okay? Anyone know another molecule? I bet you do. Second? Water is what? H2O. Okay? Another interesting one. What is hydrogen? Does anyone know it? It's a gas. It's the lightest gas that can be. It's the lightest element there is. Okay? Now, anyone know any characteristics of hydrogen? Has anyone ever heard of the Hindenburg? You haven't. You know what a dirigible is? A blimp. You know what a blimp is? Okay, a blimp. Okay, the Hindenburg, I think was German, the name sounds German anyway, was one of the very early lighter-than-air aircraft, okay? And the lightest gas that you could put in there was hydrogen, so you could lift the greatest amount and go with it. So they had made this blimp dirigible out of the Hindenburg, out of hydrogen. That was what was inside. And it was flying one night, or I think it was night, sometime, and unfortunately a storm came up. And it was sort of buffeting it around, and those things are hard to control. And nobody knows exactly what happened. Some people think it hit something, ripped the skin, and that was just enough heat for the hydrogen to combine with oxygen and explode. Because oxygen, by the way, is the thing, when something oxidizes, it gives off a lot of heat. Now, that's different from sodium. Sodium mixing with water forms sodium hydroxide, but oxygen combining with something like wood or sawdust or coal or anything else, gasoline, diesel, anything, it burns. Burns very hot. And hydrogen is one of the things that will burn very, very hot. Well, this dirigible, some other think may be lightning struck it. That was enough to, but that dirigible blew up in a fireball because there was oxygen all over in the air, hydrogen, exposed to it, some friction or just enough heat, it was a disaster, a major disaster. So why do we still have lumps today? They no longer need to fill them with hydrogen. The second lightest gas material ever is helium. A little denser than hydrogen, but it doesn't react with anything. It will not burn, it will not corrode, it will not do anything. So that all those are filled with helium. Very, very safe. Just the helium like you have in your balloons, right? Okay. And no problem there. Okay, so don't worry about being in a blender. It will not explode. So here we have an explosive gas, burns like crazy, hydrogen, combined with oxygen, which is the one element that's needed to support combustion. And what does that form when they combine chemically? Say again? Water. And what do we use water for? To put out fires. Isn't that crazy? A highly combustible gas combining with one that supports combustion, and yet when they combine together, that's what we use to put out fires. Okay? It changes things completely. Okay? So H2O is hydrogen. Is water. And there's another example of a compound. The smallest element, the smallest particle of a compound is a single molecule with two hydrogens, one oxygen. Okay? The smallest particle of an element would be the atom, because that's the smallest you could get. But for a compound, it will have all of those. Now, there is your water atom right over there. Two hydrogens, one oxygen. Isn't that a strange place to put the hydrogens? Why don't they put them on either end? They have a line there. That would make more sense, wouldn't it? Not really. Okay? You don't have to know this, but it probably would be a little bit useful to know it. For everything other than hydrogen, it likes to have 8 electrons in its outer shell. And it likes them to be 4 pairs. Okay? So this oxygen wants to have 4 pairs of electrons. It only has 6 electrons in its outer shell. So it wants 2 more. So it teams up with hydrogen, but it only has 1 electron, period. So they share one for here and share one for there, but the other 2 pairs are like this, okay? One here and one over there, because you can't, that's the only way you can get 4 pairs of electrons around a space object is 1, 2, 3, 4. They're going to be, between any 2 of them, it's an angle, and no 2 are opposite each other. So that's why water is like that. That's pretty important, okay? That makes water what we call a polar molecule. The hydrogen tends to be, because the oxygen tends to hog the electrons, so the hydrogen end of this tends to be positive, and the oxygen end tends to be negatively charged, because it tends to gather, it has, remember those 2 pairs of electrons here, plus the sharing the other 2, that leaves hydrogen just sharing 2 electrons, so it tends to be a bit positive, okay? Now, because of that, water at normal temperatures and pressures is a liquid. There's no other molecule on the earth that, with that light, oxygen has an atomic mass of 16, hydrogen 1 each, so it has a molecular mass of 18. There's no other molecule with anything close to 18 as a molecular mass that's not a gas. There are gases much heavier than that. Carbon dioxide has a carbon and 2 oxygens. It's a gas. This is 1 oxygen and 2 little hydrogen. It's a liquid. And the reason is because of that, what we call hydrogen bonding. The positive end over here, the negative end there, these molecules stick together like crazy. One molecule is attracted to the next, to the next, to the next, so they form liquids, not gases. It should be a gas, except that strong hydrogen bonding there. Okay? Now, one of the ramifications of that, have you ever jumped off either the side of the pool or a diving board into the water, but did a belly flop? Okay, I bet you did not feel like that was the most fun thing you ever did. They hurt like crazy. Why? Because water has this really strong tendency called surface tension. Those molecules do not want to let go of each other, so it's almost like hitting concrete. Not quite as bad, but it almost feels that bad. Okay? That's why when you dive, you do this kind of stuff to sort of spread the water out. People have actually broken bones diving into water, broken their neck if they get their head at a right angle. It's pretty brutal stuff. Okay. So that's a water molecule, H2O. This is a sugar molecule. This is as simple a sugar as you can get. The sort of orangey ones are carbons. It has 6 carbons, 1, 2, 3, 4, 5, 6. Okay? It has 6 oxygens. Those are the green, 1, 2, 3, 4, 5, 6. And it has 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? That is your simplest sugar you can get. Glucose. Now, slight rearrangement of that, and you've got fructose, which is what you find usually in nature. And slightly different from that is sucrose. I can't remember, but they all three are this, but they just have the way they're put together is a little different. Okay? So that's your simplest sugar going, glucose. Okay? You probably run into that medically, haven't you? You can't tell me we're out of time. Oh, my dear. Terrible. Let's see what the next slide is. Okay. We're going to talk about the makeup of these. I've already been talking about them a little bit. We'll go into more detail. Protons, electrons, and neutrons. Okay? And that's where we'll begin next time. Sorry I did too much yakking today. Okay. We'll pick up and go from there. Here's my thing. And let's see, in chapter 12, we're almost through 12.1 actually. 12.2. Goodness gracious. 12.2 is sort of long. Okay, 12.3. Then we'll look at the individual ones. 12.4. Yeah, that's it. Once I quit yakking too much, we'll get through chapter 12 pretty quickly, I think. 12.2 is a long one, though. But once we get through that, the rest will be a lot better. All right. Have a good weekend. And of course, working on physics problems will make it good, won't it? Yes. Okay.